Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we are going to start 17th lecture of Discrete Structures CSC 102. In the previous lecture we have started and discussed relations, some properties of relations. We have studied also what is the reflexive, symmetric, anti-symmetric, asymmetric and transitive relations. We have also discussed the properties of less than relations and the congruous modulo 3 relation. Today we shall continue the definitions and some other properties of relations. So today we are going to discuss transitive closure of a relation, how to combine the relations, two or more relations, how can we combine them, and how to take the composition of relations. We shall also discuss a relation induced by a partition, and then we shall move to equivalence relations, and at the end we shall discuss equivalence classes we shall made with the help of congruence modulo 3 relation. So what is basically the transitive closure of a relation? If we have a set A and a relation R on which are defined on the set A, the transitive closure of this relation is denoted by RT, R power T. This relation is also defined on the same set A that satisfy the following properties. RT must be transitive. The relation R, which is any kind of relation, it is not necessary that the relation R which we have defined on A is transitive. It is not necessary for R to be transitive. So that relation R must be subset of RT, means transitive closure of that R relation. And third property is that if S is any other transitive relation that contains R, then RT is subset of S. So what does mean this definition? It means how to make some relation R which is defined on a set A, how to make this relation R a transitive relation. So this is what we do in this definition, or this definition tells us that how can we make a relation which is not transitive. It may be transitive, but if a relation R is not transitive, then how can we make it a transitive relation? And third property tells us that the transitive relation which we made is basically the smallest possible relation, or smallest subset of the Cartesian product A cross A, which is a transitive relation. If there is some other transitive relation S, then RT must be subset of that transitive relation. So I hope you understand this. I repeat it. R is any relation on A, that is R is subset of A cross A. R is subset of A cross A. R may be transitive, R may not be transitive. So now we are going to find the transitive closure of this relation. One thing which is to be remembered here, R may or may not be transitive. So this is what you have to remember, that R is the relation on A. R is subset of A cross A, and R may be transitive or may not be transitive. Then we are going to find a transitive closure of this relation R. Then the first property of the RT is that RT must be transitive, RT must contain R, and the third property tells us this RT is the smallest possible transitive relation on R. That is, RT contains, RT is subset of A cross A, which contains least element of A cross A, which make RT a transitive relation. So next we discuss it with the help of an example. For example, we are given a set A which is 0, 1, 2, 3, and consider the relation R defined on A as follows. This is a relation which is defined on A, that is, this relation is subset of A cross A. Now, with the help of a diagram, this, which is a digraph we have studied, or directed graph we have studied in the previous lecture. If we construct a directed graph of this relation, we can construct it like this: 0, 1, 2, 3. 0 is related to 1 here, 1 is related to 2, 2 is related to 3. So we have 3 arrows here. So this is the directed graph of the given relation. Now we add some other ordered pairs which make this relation R a transitive relation. So every ordered pair must be in the RT, because R must be the subset of RT according to the first property, according to the second property of the transitive closure of a relation. So this R must be subset of RT, that is, RT must contain all these ordered pairs which are already in R. Now, how can we add least number of ordered pairs in this relation R so that it becomes a transitive relation? Since there are arrows from 0 to 1, 1 to 2, and to make it transitive, what we do here, we can see that this relation R is not transitive here in the directed graph, because 0 is related to 1, 1 is related to 2, but 0 is not related to 2, so this cannot be transitive. So how to make it a transitive relation? So for RT be a transitive closure of a relation, or RT to be a transitive relation, we must have 0 to 1, 1 to 2, and 0 to 2. 0 must be related to 2, and if we have 1 to 2, 2 to 3, we must relate 1 to 3 also to satisfy the transitive property. And now another 2 is related to 3, and 1 is related to 2, 2 is related to 3, we must have 1 to 3. And similarly, if we add up this also, 0 is related to 2 and 2 is related to 3, so we must have 0 related to 3, as here 0 is related to 2, 2 is related to 3. To satisfy the transitive property, we must have also 0 to 3. So now this relation becomes a transitive relation if we add up 0, 1 ordered pair, 1, 2, and 2, 3. And also 1, 2, 3, not 2 to 3, this is basically 1 to 3. If we add up 0 to 1, 1 to 2, not 1 to 2, this 0 to 2, 0 to 3, and 1 to 3. If we add up these 3 arrows, 1, 2, and 3, which are in red, 0 to 2, 0 to 3, and 1 to 3. if we add up these arrows, these three arrows in the given relation, which was not transitive, then this relation becomes a transitive relation. So these are basically the least number of ordered pairs which we must add in this relation, in the relation R, which was given, to make the new relation a transitive relation. We must add these three ordered pairs 0, 2, 0, 3 and 1, 3 to make the previous relation to be a transitive relation. So now one thing which is left to be checked, that whether if S is any other transitive relation that contains R, then RT must be subset of S. As we can see that here, these three arrows are the least number of arrows which make the given relation R a transitive relation. Therefore this must be a smallest possible relation which is a transitive relation. So RT, we can say that this relation is RT. We can verify, or you can verify, that if there exists some other relation S which is transitive, that then RT must be subset of that relation S. We can verify it. So now RT, we have constructed ourselves this transitive closure of the relation. We have added up the arrows in the directed graph of R so that it becomes a transitive relation. So now this is basically the smallest possible subset of A cross A, which is a transitive relation. So this is a transitive closure of a relation. Now, how to combine the relations? Relations are basically sets which contains ordered pairs. Basically R is a subset of A cross A, as we have discussed in the transitive closure of a relation. R is basically RT is also the subset of A cross A. These relations are basically subsets or sets of ordered pairs. Now if these are sets, then we must apply set operations on these sets, because there are no other operations which we can apply on sets. We can take union of two sets, we can take intersection of two sets, we can subtract a set from some other sets. So these are all operations which we can perform on the sets. So for example, if we have two sets R1 and R2 and both of them are from a set A to a set B, that is R is a relation from A to B, R1, and R2 is a relation from A to B on the same sets. So one thing is to remember here that combining relation is if we want to take the union intersection of any two relations, the one thing must be common in these relations, that is these relations must be defined on the same sets. R1 is defined on A to B, R2 is defined A to B. If here we have R3 which is defined from B to C, now we cannot take R1 intersection R3. R1 intersection R3 is not possible. This is not possible because R1 is defined on other sets, R3 is defined on some other sets. So we cannot take intersection, union or subtraction of any two relations which are defined on different sets. So to take union, intersection, subtraction and other properties of sets, all the relations must be defined on the same sets. If we take now the third thing is here, if we take intersection of two relations, the resulting relation must be some other relation, but R1 intersection R2 must be subset of R1, and as well as it must be subset of R2, which are the classical or traditional properties of sets. So as I told you, the relations are basically the sets. The relation must satisfy also all the set operations, all the properties of sets. So by taking union intersection of two sets of two relations, we must have some new relation. There is another important property, important way to combine the relation, which you have I hope you have already seen such type of relations. Composition of relations, you have already studied, I hope, composition of functions, but here we are going to discuss the composition of relations. So let R be a relation from a set A to a set B, and S be a relation from a set B to a set C. So here R is basically from A to B and S is from B to C. So how we take the composition of R and S, how we can combine these two relations if R is defined on other sets and S is defined on other set, but this is basically somewhat R must be defined from A to B and S is from B to C. This is only valid when the second set of first relation and the first set of second relation is same. Now how we construct or take the composition of R and S. Composite of R and S is the relation consisting of ordered pairs, basically AC. Now how to denote it and what are the elements of the composition of R and S? The composition of R and S basically contains the ordered pairs A and C, such type of ordered pairs where A belongs to A and C belongs to C, for which there must exist an element B such that AB is in R and BC must be in S. We denote the composition of the relation R and S by S, and there is a small circle between this, and we read it as composition of S and R, or S composition R. In other words, if relation R contains a pair AB and relation S contains a pair BC, SR contains a pair AC. S composition R is basically a new relation which we obtain. Here we have defined that R is a relation from A to B, S is a relation from B to C. Now if we take the composition of these two relations, then R, S composition R, this relation must be from A to C according to the ordered pairs of this relation. So this is how we take the composition of two relations. Now we consider an example of composition of two relations. Now we have let D and S be relations on set A. These two relations are defined on the same set A, that is D is from A to A and S is from A to A. We have these two relations, so D must be the subset of A cross A, S must be the subset of A cross A. How the relation D is defined? The D relation contains AB, ordered pairs AB, where AB belongs to A, where B must be 5 minus A, means if we choose A to be any element of A, then B must be 5 minus A. So this is a relation between the elements of the ordered pairs in D. S is another relation we have already discussed it. S contains the ordered pairs which are the elements of A cross A, such that A is less than B. So this is basically the relation or rule which is defined in this S relation. This is the rule which is defined in D. Now first of all, we shall calculate, or we shall determine the elements of D and S. Now by choosing A to be 1, the first element of A, the second element must be 5 minus 1, this is 4. If we choose 2, then this must be 5 minus 2, 3. If we choose 3 here, this 5 minus 3, 2, and 4, 5 minus 4, 1. So this is all we can choose in the relation D. Now next is S relation. What is the rule in this relation? A is less than B. Now first, if we choose 1, we cannot choose 1 here on the second place, because 1 is not less than 1. So here we choose 1, 2, 1 is less than 3, 1 is less than 4. Now we choose the second element 2. Here we cannot write 1 or 2, because 2 is not less than 1 and not less than 2. So here we write 2, 3, 2, 4, and then 3, 4. So these are all elements we can choose in S. Now how to define the composition of these two relation S composition D? S composition D basically contains those elements. First we apply D and then S. When we apply D on the ordered pairs AB, here B must be what? 5 minus A. So or we can see it here. S composition D contains AB ordered pairs such that first we apply D, and basically A is converted to B, which is 5 minus A. Now we take B as A in the S relation. This B becomes A, which is 5 minus A, and this goes to basically in the second place of S, and this must be converted to less than 5 minus A, 5 minus now 5 minus A must be less than 5 minus A must be less than B, the second element of S. So this will be converted to 5 minus A must be less than B. So this is how we can write the composition of S and D. First we apply D on the first element here. This will be converted into the second element using this relation, that is B is 5 minus A. Now the second element of D will become first element of S, as by the definition of composition of relation we have seen that R is a relation from A to B, where the first element of R is basically A, second element is B. Now B in the second relation S is basically the first element here, and the second element is C. Now in the composition A must be transformed to C, but with the help of B. S composition R, basically A will be converted to B and B converted to C. So in relation R, when we apply the R relation, we have AB. Now B is the second element here in R, but in S B will be the first element and C will be the second element. So what we have done here, A is the first element, which is, for example, 1. It will be converted to B, which is 4. Now 4 will be the first element, and the second element must be greater than 4. That is, if we have 4 here, then 4 must be this. Then we shall use this relation, the second relation. So first A is converted to 5 minus A, and then 5 minus A becomes the first element, and then 5 minus A must be less than B by using the second relation. So we shall use this relation in the composition. So here we cannot choose 1. Here we cannot choose 1 because, or you can say that we can not choose 4. We cannot choose 4 because 5 minus 4 is 1, and 1 is basically here must be less than this B. Now, or you can see here we choose only those elements whose sum must be greater than 5. So if we choose here 1 and B to be 1 or 2 or 3 or 4, we cannot have the sum of these two elements greater than 5, because 5 minus A is less than B, or we can write A plus B greater than 5. So if we write 1 here, then we can write at most 4 here. 1 plus 4 is not greater than 5, so we cannot write 1 here. We can take 2 here, 4 here, because 2 plus 4 is greater than 5. 3 we can write because it gives us greater than 5. 3 4 7 4 2 6 4 3 7 4 4 8. So these are ordered pairs which comes in the composition of S and D. So this is how we can define the composition of two relations. I hope you understand it. Now we move to the relation induced by a partition. A partition of a set A. Now first of all we must define what is a partition, then we shall define relation which we shall define relation on the partition. A partition of a set, any set A, is a finite or infinite collection of non-empty, mutually disjoint subsets whose union is the given set A. The given set is basically this. For example, if we are any set 1 to 10, we divide this set into subsets which are mutually disjoint. Mutually disjoint means if we take intersection of any two subsets of A, any two subsets, this must be empty, this must be phi. So mutually disjoint means any two subsets, कोई से भी दो सबसेट्स लें तो उनकी इंटरसेक्शन जो है वो एम्प्टी होनी चाहिए. So mutually disjoint subsets. And another property of the partition is that कि अगर हम उन तमाम सबसेट्स की यूनियन लें तो हमारे पास वही ओरिजिनल सेट A आ जाना चाहिए. So this is basically called the partition of a set. Graphically we can represent it as, if this is the whole set A, this is the whole set A, we divide it into some portions A1 2 3 4 5 6. We take the 6 subsets of the set A. Now these sets are basically mutually disjoint. If we apply the rule of Venn diagrams, here A1 don't have any common portion of A2, A2 don't have any common portion of A4. Similarly others, these sets are mutually disjoint, and if we add up these sets, if we take the union of these sets, we get the set A. So this is basically the partition of the set A. We can express it as AI intersection AJ is equal to phi whenever I is not equal to j. Means any two different sets. If we have A1 intersection A3, this must be phi. If we take the intersection of A1 and A3, this is phi. If we take the intersection of A5 with A2, this is also phi. I or j means here 1, 2 up to 6. So I must not be equal to j, means we must not take the intersection of same intersection A1. This is again A1, this is not phi. So we must take the intersection of two different sets, not the same sets. And if we take the union of A1, 2, 3 up to so on A6, this must give us the whole set E. So this is what is the partition of a given set A. Now we define the relation on which is induced by a partition. Given a partition of a set A, given a partition of a set A, the relation which we define on the partition, we define the relation R, which is defined on A as follows. For all x, y belongs to A, x is related to y if and only if, as you know, this relation is basically if and only if there is a subset AI of A which belongs to that partition, such that both x and y are in AI. Means if we have partition, and just like in the previous example, as we have A, we have divided A1, A2, A3, A4, 1, 2, 3, 4 and 5, 6. This is A1, this is A2, this is A3, this is A4, this is A5 and this is A6. If we take any two elements of A, x, y belongs to A, not A1, A2, A3, A4, 5, 6. X, y belongs to A, then x is related to y under the relation R if and only if x, y both belongs to AI. Now what is I? I is 1, 2 to 6. I may be 1, I may be 2, I may be 3, maybe 4, 5, 6. So x and y, the elements of A, must be related with each other if x, y both element belongs to the same set. For example, A2, if it may be A4, any subset. So this is how we relate two elements in this relation on the partition. For example, let A be 0, 1, 2, 3, 4, and we consider the partition 0, 3, 4, 1, 2. So these are three sets basically, 0, 3, 4, another set 1, another set 2. This is basically the partition of the set A, because it satisfies both properties of the partition. Any intersection of any two sets in this partition is empty, is phi, and union of all these subsets is equal to A. You can take the union will contain the same set A. So this is basically the partition of a set A. Now we find the relation R induced by the partition. What is the definition of the relation induced by partition? That any two elements in A are related if they belongs to the same set. Now here you can say that 0 is not related to 1. If we want to check whether 0 is related to 1 or not, no, because 0 belongs to this set and 1 belongs to this set, because these two elements belongs to different sets. So therefore we can say that 0 is not related to basically 0 is not related to 1. because 0 belongs to different set and 1 belongs to different set. So two elements, any two elements belongs to are related under this relation if they belongs to the same set. Now here we can say that 0 is related to 3, 3 is related to 0 because 0 is, why 0 is related to 3? Because 0 and 3 belongs to same set. Here 3 is related to 0 because 3 and 0 belongs to same set. 0 is related to 4, 4 is related to 0 because 0 and 4 belongs to same set. Similarly, we can write all other elements which are related to each other. 3 and 4, 4 and 3, 0 is related to 0 because both 0 and 0 are in the same set. 3 is related to 3, 4 is related to 4. Similarly, we can define 1 is related to 1, 2 is related to 2, but 1 and 2 are not related to some other elements because these are singleton sets. 1 is related to 1 because 1 and 1 both belongs to 1. Similarly, as 2 is related to 2, but 1 is not related to 2 because 1 is not related to 1, or we can write 1 is not related to or we can write 1 is, sorry, here 2, 1 is not related to 2, or we can write 1 is not related to 2. We just cross the R. This also means in some books that 1 is not related to 2. So what is the relation? Basically, now the relation contains 0 0, 0 3, 0 4, 1 1, 2 2, 3 0, 3 3, 3 4, 4 0, 4 3 and 4 4. So this is the relation which is induced by a partition we have obtained now. I hope you understand by, as we have discussed first the definition of partition and then we define the relation which is induced by partition. So next we start the equivalence relations. Next we start equivalence relations. Definition: let A be a set and R be a relation on A. R is an equivalence relation if and only if R is a reflexive, symmetric and transitive. So any relation which satisfy these three properties, that is R is reflexive, R is symmetric and R is transitive, then we say that that relation is an equivalence relation. For example, in the previous relation, which was a relation induced by a partition, this relation I write it again on the next slide here. This is basically the relation induced by a partition which we have discussed in the previous slide. Now we check whether this relation is an equivalence relation or not. First of all, A contains, A have 0, 1, 2, 3, 4, these 5 elements. A have 5 elements. Now whether all these 5 elements are related to themselves or not, to check the reflexivity, we check whether 0 is related to 0, 1 is related to 1, 2 is related to 2, 3 is related to 2, 3 is related to 3, 4 is related to 4 or not. Now here we have 0 0, 1 1, 2 2, 3 3, 4 4. So every element is related to itself under the relation R. So therefore this relation R is reflexive, as we can check it by using the directed graph. Now we have to check whether this relation is symmetric or not. Now if X is related to Y, then Y must be related to X. This is what is the definition of symmetric relation. So we check whether that 0 is related to 3, then 3 is related to 0. So until here this is symmetric. 0 is related to 4, 4 is related to 0, 3 is related to 0, 0 is related to 3, 4 is related to 0, 0 is related to 4, 4 is related to 3 here. And 3 is related to 4 also. So all the members in R, all the ordered pairs in R satisfy the symmetric property. Therefore this relation is symmetric relation. Now we have to check whether this relation is a transitive or not. So if 0 is related to 3 and 3 is related to 3, you can check it easily, I hope, because we have already studied how to check the reflexive, symmetric and transitive properties of a given relation using directed graph and some other techniques. By the definition of transitivity, if A is related to B and B is related to C, then A must be related to C. So this is what we have to check in this relation. So this relation is also a transitive relation. So this relation satisfies all the three properties of an equivalence relation, that is, this R is reflexive, R is reflexive, R is symmetric, and R is transitive. So therefore this R is an equivalence relation. This R is equivalence relation. So I hope you understand what is basically the equivalence relation. An equivalence relation on a set A must be reflexive, symmetric and transitive. Now we discuss some other examples of the equivalence relation so that you can understand well the equivalence relations. We define another relation, equivalence of digital logic circuits is an equivalence relation. How we define the relation on digital logic circuits? Let S be the set of all digital logic circuits. S be the set of all digital logic circuits which we have studied in logic with a fixed number of input. So inputs must be the same in this set. All the digital logic circuits have same inputs, that is, if there are two propositions, then they have four possibilities or four possible inputs. Define a relation E on S as follows. For all circuits C1 and C2 in S, C1 is related to C2 under the relation E. If and only if C1 has the same input-output table as C2. So two circuits, if we have two circuits C1 and C2, they are related C1E, C2, if and only if they have same input-output table. So this is what this is how we relate to digital logic circuits. Then C1 is said to be equivalent to the circuit C2. Prove that E is an equivalence relation. Now we are going to prove that E is an equivalence relation. So we have to check three properties of this relation, that whether E is reflexive, whether E is symmetric, or whether E is transitive relation. So we are going to check the first property, E is reflexive. Suppose C is a digital logic circuit in S, we must show that C is related to C. So if we have a same digital logic circuit, then the input and outputs of a same circuit are same, usually, obviously. So C is basically related to C. So this relation E is reflexive. Now we have to check the second property, which is the symmetric property of the relations. If we have C1 and C2 two relations, C1 is related to C2, then C1 and C2 have same inputs. Means C1 has input output table, C2 will have same input output table as C1. So therefore we can say that C1 is related to C2. Now obviously if C1 has input output table as C2, then C2 has input output table as C1. So we can obviously say that C2 is related to C1 under the relation E. So therefore E is symmetric. Now we have to check whether E is transitive or not. We have 3 digital logic circuit in this case. Usually how we check the transitive property: if X is related to Y and Y is related to Z, this must imply X is related to Z. So this is what we check in the transitive property of the relations. Now here we must have C is related to C1 is related to C2 and C2 is related to C3. What we have to show that C1 is related to C3, that is C1 E C3. So by definition of the relation which we define on the digital logic circuits, since C1 is related to C2, then C1 and C2 have same input output, and C2 is related to C3. If C2 and C1 have same input outputs, then C2 and C3 is also have same input output. So obviously C1 and C3 have same input output because the C2 is common in these two relations. If C2 have same input output, then C2 has same input output as C3. So obviously we have C1 have same input output as C3, so C1 is related to C3. So this relation is also a transitive relation. Therefore E is reflexive, E is symmetric, and E is transitive. Therefore E is an equivalence relation. So we have seen another example in which we prove that the relation E, which is defined on the digital logical circuits, this E is an equivalence relation. Now we are going to discuss the equivalence classes of an equivalence relation. So if some relation is an equivalence relation, then basically this relation divides the given set into classes which are called equivalence classes. Suppose, now by definition, suppose A is a set and R is an equivalence relation on A. For each element A in A, the equivalence class of A denoted by this and called the equivalence class of A, or simply class of A, is the set of all elements X in A such that X is related to A by R. That is, this class, equivalence class A, contains all those elements X of A which are related to A under the relation R, which is defined on the set A. Or we can say that for all X belongs to A, X belongs to this class if and only if X is related to A. So all those elements of A which are related to this A belongs to this class. This is what we can say briefly. To explain this, let's consider an example. Suppose we have the set A. This is 0, 1, 2, 3, 4. this is we have defined the relation R on this set A. Now we have to find the equivalence classes of the elements of A. Now R is defined as 0 0 0 4 1 1 1 3 2 2 3 1 3 3 4 0 4 4. Now we can construct the directed graph of this relation. We write 0 1 2 3 4. How we write 4 here? Because 0 is related to 4, and but 2 is not related to 4, and 1 is not related to 0. So therefore we write the elements here. Now we can say that 0 is related to 0. We construct a loop on 0. 2 is related to 2. We construct on a loop on 2, because here you can say 0 is related to 0, 1 is related to 1, 2 is related to 2, 3 is related to 3, 4 is related to 4. So at each at each element, at each point, we construct a loop, and then we see 0 is related to 4, so we construct an arrow, we draw an arrow from 0 to 4. 1 is related to 3, 1 is related to 3, so we draw an arrow from 0 to 3, 3 to 1, 4 to 0. So this is the directed graph of the given relation. Now we check whether this relation is an equivalence relation or not. कितना टाइम हो गया?
सिर्फ 51 मिनट.
अभी हाँ काफी है, ठीक है. Now we check whether this relation is an equivalence relation or not. As you can see that every element is related to itself, therefore, or you can see in the directed graph that at every element there is a loop, so therefore this relation is a reflexive relation. And if we have an arrow from one point to other point, we have an arrow from other point to the first point, so this relation is symmetric also, and this relation is also transitive. You can check it. Now we have to write the equivalence classes of this relation. Now first we write the equivalence class for 0, then for 1, then for 2, then for 3, and then for 4. We write the equivalence class, we write an equivalence class for each element of A. Now for first element 0, for 0 we write the equivalence class. We write it as 0 in the capital bracket is equal to, this class contains all those elements of A which are related to 0. Now we can see that here 0 is related to 0, 0 is related to 4, and 4 is related to 0. So the only elements which are related to 0 are 0 and 4. So this class contains 0 and 4 because no other element is related to 0. So this equivalence class contains two elements which are 0 and 0. Next, for 1 is related to 3, 3 is related to 1, 1 is related to 1. So there are only two elements which are related to 1 under the relation this. So we write 1 3. Now we write for 2. 2 is basically here. Now 2 is related to 2 itself only. There is no other element which is related to 2. So therefore this is the equivalence class of 2. Now for 3 is related to 1, 1 is related to 3. So therefore this equivalence class contains two elements which are 1 and 3. Now for 4 we have 0 and 4 are related, therefore 0 and 4, this equivalence class contains this element. Now you can notice here that the equivalence class of 0 is equal to the equivalence class of 4. Equivalence class of 1 is equal to equivalence class of 3. So the only distinct classes we have are the first class, the second and third class, and the two other classes, these are equivalent to these classes which are defined here. So we have 0 4 1 3 and 2. So the distinct equivalence classes of the given relation are 1 2 and 3. Now these three classes have basically some other properties, so we are going now to discuss those properties. So before discussing the other properties of the equivalence classes, we take another example, so that you understand well how we calculate the equivalence classes of a given set with the help of a relation. Now we take another set. Let X be the set of all non-empty subsets of 1 to 3. We have set X this 1 to 3, and X is basically the power set of this set 1 to 3. We define the relation R on X as follows. For all A and B in X, A is related to B if and only if least element of A equals the least element of B. So we define another relation on this set, which is the power set of 1 to 3. A is any two sets. Basically, this is the power set of X. Sorry, power set of this set, not X. If we say this set set A, then this X is basically the power set of A. Now the power set of A basically contains sets which are subsets of A. Now two elements of this power set X are related. A is related to B if and only if the least element of A equals the least element of B. Means सबसे छोटा A का जो एलिमेंट होगा वो B के सबसे छोटे एलिमेंट के इक्वल होगा. Means one, if we have two sets, one this set and this set, these two sets are related because in set A the least element, सबसे छोटा एलिमेंट क्या है 1. इस set B में सबसे छोटा एलिमेंट क्या है 1. So these two sets are related. This is what the relation R is between the two sets A and B. R is reflexive. First we have to check whether this given relation is equivalence relation or not, and then we shall calculate the equivalence classes of this relation. Now R is reflexive. A is related to A must be related to A. So सबसे छोटा एलिमेंट A का सबसे छोटा एलिमेंट A के इक्वल ही होगा. So therefore this relation must be reflexive. This is we can get obviously. Next we have to check whether R is symmetric or not. Suppose A and B are non-empty subsets of 1 to 3 of set A, and A is related to B. We must show that B is related to A. तो अगर A का सबसे छोटा एलिमेंट B के सबसे छोटे एलिमेंट के इक्वल है, तो B का भी सबसे छोटा एलिमेंट A के सबसे छोटे एलिमेंट के इक्वल ही होगा. So therefore this relation is also symmetric. Now we have to check whether R is transitive or not. So if we have three sets A, B, C, which are subsets of that set 1 to 3, A is related to B and B is related to C, then we have to verify that A is related to C or not. तो अगर A और B related हैं और B और C related हैं, तो A और B का जो सबसे छोटे एलिमेंट होंगे वो इक्वल होंगे. सिमिलरली B और C के सबसे छोटे एलिमेंट सेम होंगे. तो इन दोनों में B यहाँ पे कॉमन है, तो ऑब्वियसली अगर A और B का सबसे छोटा एलिमेंट सेम है तो B और C का सबसे छोटा एलिमेंट सेम होगा. सो A और C का भी सबसे छोटा एलिमेंट सेम होगा. So therefore we can say that A is related to C. So this relation is an equivalence relation because this relation R is reflexive, symmetric and transitive. Now we are going to find the equivalence classes of this relation. The equivalence class of 1, we shall first find the equivalence class of 1. This contains basically all those sets which have least element equal to 1. So this 1 is related to 1. This set, this contains this set, this contains this set, this contains this set, because all the least element of these sets are equal, which are 1. Now the equivalence class for 2 which contains this set, because the least element in these two sets is 2. Now for this element, the equivalence class contains only this set, because there is no other set in which the least element is 3. So we have this equivalence class, this equivalence class, and this equivalence class. This is how we can calculate the equivalence classes of a relation. For today, I think it's enough, and in the next lecture we shall discuss some other properties of the equivalence relation, and then the properties of the equivalence classes. What we have discussed today, we have defined a relation induced by a partition. We have also discussed the transitive closure of a relation, and then we have studied the equivalence relations on sets. An equivalence relation is, as I have told you, that a relation which is transitive, symmetric, and reflexive is an equivalence relation. We have also discussed the equivalence classes, how to calculate or construct the equivalence classes of a relation. So for today it is enough. In the next lecture we shall study some other properties of the equivalence relation and of the equivalence classes. So till the next lecture, Allah Hafiz.